We need to be more data-driven. The phrase every executive loves to say, but few know how to actually implement. The problem isn't collecting data, it's knowing which type of analytics to use when. Are you just describing past performance, or are you actually prescribing future actions? Today, I'm breaking down the 4 types of analytics that every data professional needs to master. This isn't just theoretical. I'll show you exactly when to use descriptive, diagnostic, predictive, and prescriptive analytics with real business examples that you can apply immediately to your own work. Here's something you may find shocking. Most data professionals, the very people companies rely on to make sense of their information, can't correctly distinguish between the 4 fundamental types of analytics. And I'm not talking about entry-level analysts here. This knowledge gap extends to seasoned professionals across industries who work with data every day. Why does this matter? Because in today's business landscape, making decisions without understanding which analytics approach you need is like trying to build a house without knowing the difference between a hammer and a saw. You might eventually get something constructed, but it won't be what you envisioned, and it'll take much longer than necessary. The confusion typically starts with a common misconception. Many professionals believe that analytics simply means having dashboards and reports. They equate the entire discipline with its most basic function, descriptive analytics, without recognizing that this is merely the foundation of a much more complex and valuable pyramid of capabilities. This limited understanding isn't just an academic problem, it translates directly to financial consequences. Organizations are losing millions in missed opportunities because they're using rudimentary approaches to answer sophisticated questions. Imagine a retailer trying to determine which products to stock next season. If they're only looking at historical sales reports, descriptive analytics, rather than using predictive models to forecast future demand, they're essentially driving while only looking in the rearview mirror. Consider a mid-sized manufacturing company that invested heavily in dashboard technology. They spent months building beautiful visualizations showing production metrics and inventory levels. Yet, when the CEO asked why certain product lines were underperforming and what they should do about it, the analytics team couldn't provide answers. They had invested all their resources in descriptive tools that could show what was happening, but nothing that could explain why or recommend actions. The result, continued underperformance and eventually discontinuation of product lines that might have been salvageable with the right analytics approach. Or take a healthcare provider that used basic reporting to track patient readmissions. They knew their rates were above industry averages, but couldn't identify the underlying causes or predict which patients were at highest risk. Without moving beyond descriptive analytics to diagnostic and predictive approaches, they continued investing in broad-based interventions that helped some patients but missed many of the most vulnerable ones. The cost in both patient outcomes and financial penalties was substantial. These examples highlight a crucial reality. There's a vast chasm between collecting data and extracting actionable value from it. Many organizations have become proficient at amassing information, customer behaviors, operational metrics, financial indicators, but significantly fewer have developed the capability to transform that information into insights that drive decisions. This knowledge gap creates a cascade of problems throughout organizations. Teams invest in expensive data infrastructure without clear plans for how it will generate returns. Analysts spend countless hours producing reports that executives glance at but can't act upon. Data scientists build sophisticated models that don't answer the business questions that matter most. all because there's confusion about which type of analytics is needed for which purpose. The confusion also leads to poor resource allocation. Companies might invest heavily in advanced machine learning capabilities, predictive analytics, when they haven't even mastered the fundamentals of understanding why certain patterns exist in their data, diagnostic analytics. It's like trying to run before you can walk, inevitably leading to stumbles and falls. Strategic decisions suffer similarly. How can an organization develop an effective data strategy if the leadership team doesn't understand the progression of analytical capabilities? They might set unrealistic expectations. We'll use AI to optimize all our business processes next quarter, or miss opportunities to extract value from existing data assets before investing in new ones. To address this widespread confusion, we need a clear framework that illustrates how different types of analytics build upon each other. This is where the analytics evolution pyramid becomes invaluable. This framework shows how analytics capabilities develop progressively, starting with descriptive, what happened, moving to diagnostic, why did it happen, then predictive, what will happen, and finally reaching prescriptive, what should we do. Each level of the pyramid represents not just different techniques and technologies, but fundamentally different questions that organizations can answer with their data. And critically, each level depends on the ones below it. You can't effectively predict future outcomes without first understanding what happened in the past and why those patterns occurred. So, why do so many professionals struggle to distinguish between these four types? There are several reasons. First, these concepts aren't typically taught comprehensively in traditional educational programs. Even data science curricula often focus more on techniques and tools than on the business context in which they're applied. Second, vendors and consultants frequently blur the lines between analytics types in their marketing materials, claiming their solutions offer advanced analytics without clearly defining what that means. This creates confusion about which capabilities are truly being offered. Third, the field is evolving rapidly. Techniques that were once considered advanced predictive approaches are now routine. Artificial intelligence and machine learning are creating new possibilities at the prescriptive level. This constant evolution makes it challenging for professionals to maintain a clear understanding of where different approaches fit in the overall landscape. Fourth, many organizations operate in silos with different teams responsible for different types of analytics. The reporting team handles descriptive analytics, data scientists work on predictive models, and business analysts conduct diagnostic investigations. Without cross-functional collaboration, no one develops a holistic view of how these approaches complement each other. Finally, there's often pressure to jump straight to advanced analytics without building the necessary foundation. Executives read about artificial intelligence transforming industries and want similar capabilities immediately, not understanding that effective AI implementations typically require strong descriptive and diagnostic analytics as prerequisites. The result of these factors is a professional landscape where many data practitioners have deep expertise in specific techniques, but lack the broader context of how different analytics approaches fit together. They might be experts in developing dashboards or building machine learning models, but they struggle to articulate when each approach is appropriate or how they build upon each other. This confusion doesn't just affect individual careers, though it certainly does that. It impacts entire organizations' ability to generate value from their data investments. Companies that understand the progressive nature of analytics capabilities can develop strategic roadmaps that build capabilities systematically. Those that don't often find themselves with expensive tools that don't deliver the insights they need. The good news is that this confusion can be resolved through a clear understanding of the analytics evolution pyramid. By recognizing that each type of analytics serves different purposes, answers different questions, and requires different skills and technologies, organizations can develop more effective data strategies and professionals can better position their expertise. The foundation of the analytics evolution pyramid isn't just a starting point, it's the critical platform upon which all other data capabilities are built. Despite collecting mountains of historical data, many organizations fail to transform these records into meaningful insights that accurately answer the seemingly simple question, what actually happened? Imagine this scenario. Your CEO walks into your office unannounced and asks, how did we perform last quarter? Your instinct might be to pull up dashboards showing sales figures, revenue trends, customer acquisition numbers, and other key performance indicators. This reaction points directly to descriptive analytics, the first and most fundamental level of the analytics pyramid. Descriptive analytics is defined as the process of summarizing historical data to understand what happened. It's the practice of examining past performance through the lens of quantifiable metrics. While this might sound basic, don't be deceived by its apparent simplicity. Without a solid foundation of descriptive analytics, attempting to implement more sophisticated analysis is like building a house on sand. Think about it this way. How can you possibly diagnose why your customer churn increased if you haven't accurately measured what that increase was in the first place? How can you predict future sales trends without a clear picture of historical sales patterns? The answer is simple. You can't. What makes descriptive analytics particularly challenging isn't the concepts themselves, but the execution. It requires meticulous attention to several key components. First, there's data collection, ensuring you're gathering the right information from all relevant sources. Many companies struggle here, collecting either too much irrelevant data or missing critical pieces altogether. Next comes data cleaning, perhaps the most underappreciated yet crucial step. Raw data is inherently messy, containing duplicates, errors, and inconsistencies that can severely distort analysis. A thorough cleaning process transforms raw numbers into reliable information. Without this step, even the most sophisticated analysis will yield misleading results. The classic garbage in, garbage out scenario. The third component involves data summarization, condensing large volumes of information into meaningful aggregations that highlight important patterns and trends. This might include calculating averages, percentages, totals, or growth rates that provide meaningful context to raw figures. Finally, there's visualization, converting numerical summaries into charts, graphs, and dashboards that make the information accessible to stakeholders across the organization. Effective visualization transforms numbers into stories that resonate with decision makers, bridging the gap between data and action. Let's look at real-world applications of descriptive analytics that you likely encounter regularly. Monthly sales reports break down performance by product lines, regions, and customer segments, highlighting top performers and areas of concern. Website traffic dashboards display visitor counts, page views, bounce rates, and conversion metrics, helping marketing teams understand audience behavior. Inventory management systems track stock levels, turnover rates, and out-of-stock incidents, enabling supply chain optimization. What makes these examples powerful isn't their complexity, but their clarity in answering specific business questions. A well-designed sales dashboard doesn't just show numbers, it reveals whether the new product launch met expectations, if the Eastern region is still outperforming other territories, or whether the seasonal promotion drove the anticipated revenue spike. Consider a retail business analyzing its sales trends over time. Descriptive analytics would reveal fluctuations in sales volumes, peak shopping days, best-selling products, and customer spending patterns. These insights might show that sales typically increase by 40% during holiday weekends, that electronic accessories consistently outperform other departments, or that in-store transactions average 15% higher value than online purchases. Other common descriptive metrics and KPIs include profit margins. Are we making more or less money per sale? Customer acquisition rates. How many new customers are we gaining? And operational efficiency measures. How quickly are we fulfilling orders? These metrics serve as vital signs for an organization's health, alerting management to potential issues before they become critical problems. What's particularly striking is that approximately 70% of organizations remain at this descriptive analytics stage. Many companies invest heavily in data collection systems but struggle to progress beyond basic reporting. They have the raw materials but lack the tools or expertise to extract deeper value. The reasons for this stagnation vary. Sometimes it's a matter of organizational culture. Businesses become comfortable with their existing reporting and don't see the need to advance further. Other times it's a skills gap. Moving beyond descriptive analytics requires different capabilities and mindsets. Most commonly, it's because companies haven't fully mastered descriptive analytics itself, making attempts to progress premature. Here's where many organizations go wrong. They underestimate the importance of getting descriptive analytics right. They view it as merely the first step, something to rush through on the way to more sophisticated analysis. This perspective misses a crucial truth. Descriptive analytics isn't just a stepping stone, it's the foundation upon which all subsequent analysis stands. Poor descriptive analytics creates a ripple effect throughout the entire analytics ecosystem. Inaccurate historical data leads to faulty diagnoses, which lead to unreliable predictions, which ultimately result in harmful prescriptions. Think of it as a medical analogy. If a doctor records your temperature incorrectly, they might misdiagnose your condition, make incorrect predictions about your recovery, and prescribe inappropriate treatments. Across industries, effective descriptive dashboards showcase the power of this fundamental analytics type. Retail executives examine sales performance metrics to identify product momentum and inventory challenges. Healthcare administrators monitor patient outcomes and facility utilization rates to optimize care delivery. Financial institutions track transaction volumes and account balances to maintain operational control. Transportation companies analyze fleet performance and route efficiency to control costs. What separates organizations that extract genuine value from descriptive analytics versus those merely collecting digital dust on their dashboards? The difference lies in their approach to implementation. Successful companies recognize that effective descriptive analytics requires careful thought about what metrics truly matter, how they should be calculated, and how they connect to business objectives. Consider these questions when evaluating your descriptive analytics foundation. Are you measuring the right things? Do your metrics directly connect to business objectives? Is your data accurate and consistent? Can stakeholders easily access and understand the information? Are your visualizations revealing meaningful patterns rather than just displaying numbers? The limitations of descriptive analytics are important to acknowledge. While it excels at telling you what happened, it doesn't explain why those events occurred. It can show that customer complaints increased by 30% in March, but not why customers became dissatisfied. It can reveal that conversion rates dropped following a website update, but not what specific changes caused visitors to abandon their purchases. Similarly, descriptive analytics cannot predict future outcomes or recommend optimal actions. It's retrospective by nature, offering a rearview mirror perspective rather than a forward-looking one. Understanding these limitations isn't about diminishing the value of descriptive analytics, but recognizing when you need to complement it with other approaches. Despite these constraints, mastering descriptive analytics delivers tremendous value. It establishes a single source of truth within organizations, aligning teams around consistent metrics and definitions. It creates transparency, making performance visible and accountable. It identifies patterns and anomalies that might otherwise go unnoticed. Perhaps most importantly, it sparks the questions that drive deeper investigation. Those questions sparked by descriptive data often lead to the most transformative business insights. Consider that famous retail discovery where an unexpected correlation between diaper and beer sales completely transformed store layout strategies. Welcome to the world of diagnostic analytics, where the what finally meets the why. Imagine this scenario. Your company's quarterly report shows sales plummeting 15% across all regions. Your descriptive analytics dashboard faithfully displays this alarming trend in colorful charts and graphs. You can see exactly what happened, but the most crucial question remains unanswered. Why did it happen? This is precisely where diagnostic analytics enters the picture. Diagnostic analytics is fundamentally about investigation, examining data to answer that critical "why did this happen?" question. It moves beyond merely reporting events to uncovering their root causes. Think of descriptive analytics as the detective who documents the crime scene, while diagnostic analytics is the investigator who pieces together the evidence to solve the case. What's particularly concerning is how many organizations invest substantially in building descriptive capabilities, but never advance to this diagnostic stage. They meticulously track metrics, create sophisticated dashboards, and circulate regular reports. Yet, when anomalies appear, they're left with speculation rather than explanation. These companies essentially have smoke detectors without fire extinguishers. They can identify problems but lack the tools to understand them. The diagnostic toolkit contains several powerful techniques that transform raw data into meaningful explanations. Drill-down analysis, for instance, allows analysts to break down broad metrics into increasingly granular segments until they locate the source of a problem. A company might start by analyzing profit margins across all product categories, then progressively narrow focus to specific subcategories, and finally to individual products. Perhaps discovering that a single underperforming product is dragging down an entire division's numbers. Correlation analysis represents another essential diagnostic method, examining relationships between variables to identify potential causal links. Remember that diaper-beer connection? This wasn't just an amusing coincidence, it revealed important customer behavior patterns that informed merchandise placement decisions. By understanding these relationships, businesses can make informed decisions about everything from product placement to promotional strategies. Data mining provides yet another approach, allowing analysts to sift through vast quantities of information to discover hidden patterns and trends. Through sophisticated algorithms, data mining can reveal clusters of similar behaviors, unusual outliers, or unexpected relationships that might explain particular business outcomes. This technique proves especially valuable when dealing with massive data sets where manual analysis would be impractical. Root cause analysis rounds out the diagnostic toolkit by systematically tracing problems back to their origin. Rather than addressing symptoms, this approach identifies and remedies fundamental issues. It's the difference between continually treating a recurring fever and diagnosing the underlying infection that causes it. Let me share a real-world application that illustrates how diagnostic analytics creates tangible business value. Consider a retail chain that identified a sudden spike in vegan product sales. Their descriptive analytics clearly showed the trend. Sales had increased dramatically over the previous quarter. But why? Through diagnostic analysis, they discovered that recent marketing campaigns emphasizing health benefits had resonated particularly well with a specific customer segment. This insight allowed them to adjust inventory and marketing strategies accordingly, maximizing the opportunity they might otherwise have misunderstood. In another example, a subscription-based service was experiencing troubling customer churn. Their descriptive metrics clearly showed subscribers leaving but offered no explanation. By applying diagnostic analytics to customer feedback and behavior data, they uncovered specific pain points, confusing pricing tiers, service outages during peak usage times, and a complicated cancellation process. This diagnosis enabled targeted improvements that significantly reduced cancellations over the following quarters. What makes diagnostic analytics particularly powerful is how it transforms raw statistics into contextual understanding. Without this context, businesses often misinterpret data or draw incorrect conclusions. Imagine a software company noticing increased customer support tickets after a recent update. Descriptive analytics simply reports the increase, but diagnostic analytics might reveal that most tickets come from users on a specific browser version experiencing compatibility issues, a much more actionable insight than the mere fact that tickets increased. Statistical methods form the backbone of effective diagnostic analysis. Techniques like regression analysis help quantify relationships between variables, determining whether connections are coincidental or truly significant. Hypothesis testing allows analysts to systematically evaluate potential explanations, separating genuine factors from statistical noise, and visualization tools help make these complex relationships understandable to decision makers who may lack technical expertise. The transition from descriptive to diagnostic analytics represents a fundamental shift in organizational thinking. Instead of simply tracking metrics, companies begin asking deeper questions, moving from what's happening to why is it happening. This evolution transforms data from a passive recording of events into an active tool for business intelligence. It's like upgrading from a security camera that merely documents incidents to a sophisticated system that analyzes behaviors and identifies potential problems before they escalate. Despite its tremendous value, diagnostic analytics does come with challenges. First, it requires more sophisticated data infrastructure than basic descriptive reporting. Organizations need systems that can integrate information from multiple sources, apply complex analytical techniques, and support interactive exploration of results. Second, effective diagnosis demands both technical skills and domain expertise. Analysts must understand not just how to manipulate data, but also the business context in which that data exists. Finally, diagnostic analytics places greater demands on data quality. Incorrect or incomplete information that might be tolerable in summary statistics becomes problematic when conducting detailed investigations. This explains why many organizations struggle to progress beyond descriptive capabilities. They hit roadblocks in terms of data integration, analytical talent, or executive understanding of what's possible. Some become trapped in analysis paralysis, continually investigating without reaching actionable conclusions. Others make the opposite mistake, jumping to conclusions without thoroughly examining alternative explanations. Finding the balance rigorous enough to be accurate but practical enough to be useful, represents a significant organizational challenge. What fundamentally distinguishes diagnostic from descriptive analytics is the difference between observation and understanding. Descriptive analytics tells you your temperature is elevated. Diagnostic analytics explains why you have a fever. Descriptive shows that customers are abandoning shopping carts. Diagnostic reveals they're leaving because shipping costs appear too late in the checkout process. Descriptive identifies the anomaly. Diagnostic explains its origin. This distinction has profound implications for business decision-making. With only descriptive capabilities, organizations react to symptoms rather than addressing causes. They might respond to declining sales by blindly increasing marketing spend, when diagnostic analysis might reveal that product quality issues are driving customers away, a problem no amount of marketing can fix. Effective diagnosis allows for targeted interventions that address root causes rather than superficial manifestations. It's worth noting that diagnostic analytics primarily examines historical data. It looks backward to explain what has already occurred. While this historical focus provides valuable insights, it doesn't directly predict future outcomes or prescribe specific actions. This limitation points to the need for more advanced analytics approaches when organizations want to move beyond explanation to prediction and optimization. But those capabilities must build upon the solid diagnostic foundation. While diagnostic analytics helps us understand the past, what if your organization could actually anticipate the future? Despite the clear value of predictive capabilities, a surprisingly small percentage of companies successfully make this transition. Most remain trapped in the rearview mirror of historical data analysis. This critical juncture represents the most fundamental shift in the analytics journey, moving from explaining what happened to forecasting what will happen next. Think about it. Would you rather know why sales dropped last quarter or predict which customers are about to leave before they actually do? This shift from reaction to anticipation doesn't just represent an evolution in technical capability, it requires a complete transformation in organizational thinking. It's the difference between being a historian and becoming a futurist. The transition from diagnostic to predictive analytics represents a pivotal moment where companies must embrace a fundamentally different approach to data. Unlike the backward-looking nature of the first two analytic stages, predictive capabilities demand organizations adopt a forward-thinking mindset. This shift isn't merely about implementing new tools, it's about reimagining how the entire organization views and utilizes data. Many leaders struggle with this transition because it requires significant changes in how teams operate. Where descriptive and diagnostic analytics focus on explaining events that have already occurred, predictive approaches demand comfort with probability and uncertainty. Employees accustomed to definitive answers about past performance must learn to trust statistical models that deal in likelihoods rather than certainties. This mindset shift extends beyond the analytics team. Business leaders must learn to incorporate predictive insights into their decision-making processes, often challenging long-standing intuitions or traditions. The entire organization needs to develop what we might call probabilistic thinking, the ability to make decisions based on likely outcomes rather than historical precedents alone. The technical requirements also change dramatically at this stage. While descriptive and diagnostic analytics often rely on structured data and SQL queries, predictive approaches typically demand more advanced tools and techniques. Organizations suddenly need expertise in statistical modeling, machine learning algorithms, and programming languages like Python or R. The infrastructure requirements shift as well, with greater needs for processing power, specialized software, and integrated data pipelines. But perhaps the most challenging aspect is the personnel transition. Successful predictive analytics requires a different skill set than earlier stages. Companies need data scientists who understand advanced statistical methods, software engineers capable of deploying models into production environments, and domain experts who can guide model development and interpret results. This talent gap represents one of the most significant barriers organizations face when attempting to advance their analytics capabilities. It's particularly telling that many organizations attempt to leapfrog directly to predictive analytics without establishing a solid foundation. This approach almost inevitably leads to failure. Without robust descriptive capabilities, they lack the clean, consistent data needed for effective modeling. Without diagnostic expertise, they struggle to identify the meaningful variables that should inform their predictions. The result is often expensive analytics initiatives that produce unreliable or unusable results. Statistics reveal the difficulty of this transition. Only a small percentage of companies successfully implement predictive analytics, with the vast majority remaining stuck at descriptive and diagnostic levels. This isn't surprising when we consider the comprehensive organizational changes required. Successfully moving into predictive territory demands more than just technological investment. It requires significant cultural transformation and capability building. Organizations that rush into predictive analytics without proper preparation typically encounter several common obstacles. First, they often lack the necessary historical data to train effective models. Predictive algorithms require substantial amounts of clean, relevant data covering various conditions and outcomes. Companies that haven't invested in systematic data collection and management find themselves without the raw materials needed for prediction. Second, unprepared organizations frequently underestimate the expertise required. They might hire data scientists without creating the supporting infrastructure these specialists need to succeed. Or they might invest in sophisticated modeling tools without developing the internal knowledge to use them effectively. Either way, the result is technical capabilities that remain underutilized or produce unreliable results. Third, organizations often fail to integrate predictive insights into actual decision-making processes. They develop forecasting models that generate interesting predictions, but never connect these insights to operational workflows where they could drive value. The models become academic exercises rather than business tools, eventually losing support as stakeholders question their practical utility. The preparation needed before effectively implementing predictive analytics is substantial but often overlooked. Organizations must first ensure they have robust data collection mechanisms capturing all relevant variables. They need data governance frameworks that maintain quality and consistency. They require the technical infrastructure to store and process larger volumes of data more rapidly. And perhaps most importantly, they need to develop a data-driven culture where employees at all levels understand and value analytical insights. Developing this foundation doesn't happen overnight. It requires deliberate investment and consistent leadership focus. Companies that successfully navigate this transition typically take an incremental approach, starting with smaller predictive projects that build on existing strengths. They might begin by forecasting well-understood metrics using established analytical techniques before advancing to more complex predictions or sophisticated algorithms. This methodical approach yields multiple benefits. It allows organizations to develop capabilities gradually, learning from each project before tackling more ambitious initiatives. It demonstrates value early, building organizational support for further investment. And it identifies specific challenges in the existing analytics infrastructure, highlighting where additional resources or expertise might be needed. The companies that successfully make this transition share common characteristics. They invest in developing data literacy across the organization, ensuring that both technical and business teams speak a common language. They create cross-functional teams that combine analytical expertise with domain knowledge. They implement governance structures that maintain data quality while enabling innovation. And they establish clear connections between analytical insights and business outcomes, ensuring that predictive capabilities directly support strategic objectives. Without these foundational elements, organizations risk making several critical mistakes when attempting to implement predictive analytics. They might invest in sophisticated tools without the expertise to use them effectively. They could develop models that solve interesting technical problems but address no actual business needs. Or they might produce predictions that business leaders don't trust or understand, preventing the insights from influencing decisions. Perhaps the most common mistake is underestimating the organizational change required. Technical leaders often believe that implementing predictive capabilities is primarily a matter of acquiring the right tools and hiring specialized talent. But the reality is that successful predictive analytics requires changes across the organization, from how data is collected and managed to how decisions are made and performance is measured. This explains why many organizations attempt to skip foundational analytics stages and jump directly to predictive capabilities, only to face failure. Without the necessary historical data and insights to inform their models, they're essentially building on sand. The predictive models might produce outputs, but those outputs lack reliability or business relevance. Resources are wasted and confidence in analytics initiatives erodes. Even when organizations recognize the need for preparation, they often underestimate the investment required in training and tools. Companies need to develop data literacy among staff and establish a genuine data-driven culture where employees at all levels understand and value analytical insights. This cultural shift doesn't happen automatically. It requires dedicated effort, executive sponsorship, and ongoing reinforcement. The transition from diagnostic to predictive analytics necessitates a fundamental shift in mindset. Organizations must prioritize foresight and proactive decision-making over merely understanding past performance. This requires comfort with statistical concepts like confidence intervals and probability distributions. It demands willingness to act on insights that may conflict with established practices or intuitions. And it needs patience, as building predictive capabilities takes time and typically involves learning from initial failures. The rewards, however, are substantial. Organizations that successfully make this transition gain the ability to anticipate market changes before competitors. They can identify problems before they manifest, addressing potential issues proactively rather than reactively. They can allocate resources more efficiently, directing investments toward opportunities with the highest probability of success. And they can develop more resilient strategies that account for various possible futures rather than assuming the continuation of historical patterns. How can you identify which customers are about to leave your business before they show any obvious signs of dissatisfaction? This question represents the powerful shift from understanding past events to anticipating future behaviors, a capability that transforms reactive businesses into proactive market leaders. The science of prediction isn't about perfect foresight, but rather about probability-based insights that consistently outperform human intuition, even with imperfect data. Predictive analytics uses historical data, statistical algorithms, and machine learning techniques to identify patterns and forecast future outcomes. Unlike diagnostic analytics that explains why something happened, predictive analytics focuses on what might happen next. This approach transforms uncertainty into actionable business intelligence by calculating probabilities of specific events occurring based on patterns discovered in your historical data. The business value of accurate prediction is immense. Consider customer churn, the costly problem of customers abandoning your product or service. Traditional approaches rely on obvious warning signs like complaints or declining usage, but by then it's often too late. Predictive models can identify subtle behavioral patterns that human analysts would never detect, allowing you to intervene before customers make the decision to leave. However, this power comes with significant complexity. Effective predictive analytics requires a blend of statistical expertise, domain knowledge, and technical implementation skills. Organizations must invest in specialized talent capable of building and interpreting these models. They need robust data infrastructure to support the substantial computational requirements. And perhaps most challenging, they must develop organizational processes that can quickly act on the predictions generated. Several key techniques form the foundation of predictive analytics. Regression analysis examines relationships between variables to forecast numerical outcomes, like predicting next month's sales based on factors such as seasonality, marketing spend, and economic indicators. Machine learning models use algorithms that automatically improve through experience, identifying complex patterns in data that traditional statistical methods might miss. Time series forecasting specifically analyzes data points collected over time to project future values, crucial for understanding seasonal trends or cyclic behaviors. Customer churn prediction represents one of the most valuable applications of predictive analytics. By analyzing historical purchase patterns, support interactions, website behavior, and other customer data points, these models can identify which customers are at risk of leaving. This allows businesses to implement targeted retention strategies before customers actually depart, a capability that dramatically improves customer lifetime value. PCAN, Predictive Customer Analytics, exemplifies how modern tools are making predictive capabilities more accessible. This platform allows users without extensive data science expertise to build effective predictive models. Using PCAN, a business could formulate a predictive question like, predict monthly which customers will stop making purchases in the next month. The system then helps translate this business question into a model specification. Let me walk you through how this works in practice. First, you would upload your historical customer data, including purchase histories, demographic information, and interaction records. PCAN's generative AI features assist in formulating the precise predictive question and generating the SQL notebooks needed for model training. The system then analyzes your data to identify patterns that precede customer departure. For example, the model might discover that customers who reduce their purchase frequency by 30% over 2 consecutive months, while also visiting your support site, are significantly more likely to churn in the following month. These subtle pattern combinations would be virtually impossible for a human analyst to detect consistently across thousands or millions of customers. Once trained, the model evaluates performance using metrics like precision, the percentage of customers flagged as likely to churn who actually do churn. A precision of 66.4%, as demonstrated in real-world applications, means that 2/3 of the customers flagged by the model will indeed stop purchasing. This performance significantly outpaces rule-based approaches or random guessing, which typically achieve much lower precision rates. The practical implications are substantial. Rather than spreading retention resources thinly across your entire customer base, you can focus on the subset of customers the model identifies as high risk. This targeted approach dramatically improves the ROI of retention efforts while simultaneously enhancing customer satisfaction through more relevant engagement. Effective predictive modeling requires understanding the critical distinction between correlation and causation. Correlation simply indicates that two variables tend to move together, like ice cream sales and swimming pool visits both increasing during summer months. Causation, however, implies that one variable directly influences another, like price reductions causing increased sales. Predictive models primarily leverage correlations to make forecasts. They identify patterns that frequently precede certain outcomes without necessarily establishing why these relationships exist. This limitation means that while predictive analytics excels at answering what is likely to happen, it doesn't inherently tell you why it will happen or what you should do about it. For instance, a model might accurately predict which customers will churn, but won't automatically tell you the most effective intervention for each customer. That's where human judgment and business expertise remain essential, interpreting predictions in context and determining appropriate actions. This highlights an important principle. Predictive analytics isn't about replacing human decision-making, but enhancing it with data-driven insights that overcome our cognitive limitations and biases. The most successful implementations combine algorithmic predictions with human expertise. Implementation challenges extend beyond technical considerations. Organizations must prepare for the cultural shift predictive capabilities require. Employees accustomed to making decisions based on past performance or intuition may resist relying on probabilistic forecasts. Leaders must foster understanding of how these models work and establish processes for incorporating their insights into operational decisions. Building effective predictive capabilities typically follows an incremental approach. Organizations often begin with focused projects addressing specific high-value business questions before expanding to more complex applications. This gradual approach builds organizational confidence in predictive techniques while developing the necessary skills and infrastructure. The transformative power of predictive analytics stems from how it fundamentally changes an organization's relationship with the future. Rather than reacting to events after they occur, businesses can anticipate changes and take preemptive action. This proactive stance creates competitive advantages that compound over time as the organization develops increasingly sophisticated predictive capabilities. That proactive stance enabled by prediction becomes truly transformative when paired with automated decision intelligence. While many organizations can now forecast customer behaviors with reasonable accuracy, only a small percentage have systems that automatically determine the optimal response to those predictions. This final evolution in the analytics journey, prescriptive analytics, bridges the critical gap between foresight and action. What if your analytics could not just predict a problem, but tell you exactly how to prevent it? Imagine having a system that doesn't merely flag that a manufacturing component is likely to fail within the next 48 hours, but simultaneously calculates the exact maintenance window that would minimize production disruption, identifies which technician is optimally positioned to perform the repair, and automatically schedules the work order. This isn't science fiction, it's prescriptive analytics in action. Prescriptive analytics represents the pinnacle of the analytics evolution pyramid, answering the essential question, what should we do? While predictive analytics gives you probabilities of future outcomes, prescriptive analytics takes those predictions and translates them into recommended actions designed to optimize business outcomes. It's the difference between knowing a storm is coming and having a detailed evacuation plan with optimized routes based on real-time traffic conditions. What makes prescriptive analytics particularly valuable is how it combines multiple disciplines to create decision support systems that can navigate complex scenarios with countless variables and constraints. These systems can evaluate thousands of possible decision paths and identify the optimal course of action in situations where human intuition would be overwhelmed by the complexity. Consider a hospital struggling with emergency room overcrowding. Predictive models might accurately forecast patient volumes for the next 24 hours, but prescriptive analytics would take that forecast and generate specific staffing recommendations, suggest optimal patient transfer protocols between departments, and even identify which elective procedures could be safely rescheduled to free up resources, all while balancing numerous constraints like staff certification requirements, equipment availability, and patient care standards. The technical sophistication required for effective prescriptive analytics explains why it sits at the top of the analytics pyramid. Unlike simpler forms of analysis, prescriptive systems employ a variety of advanced techniques. Optimization algorithms can determine the most efficient allocation of limited resources across competing priorities. Simulation models can play out thousands of what-if scenarios to identify robust solutions that perform well across different potential futures. Decision trees can map complex choice pathways to find optimal decision points. And increasingly, AI-powered recommendation engines can learn from past decisions to continuously improve their suggestions. These techniques aren't merely theoretical, they're delivering measurable business value across industries. The travel sector offers perhaps the most visible example through dynamic pricing strategies. When you book a flight or hotel room, the price you see isn't arbitrarily set. It's the output of sophisticated prescriptive systems analyzing countless factors, including current booking levels, historical patterns, competitor pricing, search trends, and even weather forecasts. These systems don't just predict demand, they calculate the exact price point that maximizes revenue while maintaining competitive occupancy rates. Healthcare provides another powerful illustration of prescriptive analytics potential. Advanced medical systems now combine patient data with treatment protocols and predictive models to recommend personalized care plans. These systems can analyze a patient's medical history, genetic markers, lifestyle factors, and treatment responses to suggest interventions with the highest probability of success while minimizing side effects. Beyond individual patient care, hospital operations benefit from prescriptive systems that optimize everything from surgical scheduling to medication inventory management. What makes prescriptive analytics fundamentally different from other forms is how it integrates business rules and constraints with predictive insights. A retailer's prescriptive inventory system doesn't just forecast that demand for winter coats will increase by 40% next month. It translates that prediction into specific ordering recommendations that account for warehouse capacity, supplier lead times, cash flow constraints, and even environmental sustainability targets. The system weighs multiple competing objectives simultaneously to arrive at balanced recommendations that reflect the organization's strategic priorities. The return on investment from well-implemented prescriptive analytics can be substantial. Organizations that successfully deploy these systems often report significant efficiency gains and profitability improvements compared to those relying on less sophisticated analytics approaches. The competitive advantage comes from being able to make consistently optimal decisions across thousands of small choice points, where the cumulative impact creates meaningful separation from competitors. The emergence of artificial intelligence has dramatically expanded the potential of prescriptive analytics. Machine learning algorithms can now process vast data sets to identify complex patterns that would elude traditional statistical methods. These AI-powered systems can adapt and improve their recommendations over time as they observe the outcomes of previous decisions. For instance, an AI-driven marketing optimization system might continuously refine its understanding of which promotional offers work best for different customer segments under varying market conditions, automatically adjusting its recommendations as consumer preferences evolve. However, implementing truly effective prescriptive analytics requires substantial organizational capability. The technical infrastructure needs are significant, from data integration systems that combine information from disparate sources to computational platforms capable of running complex algorithms at scale. Even more challenging is developing the human expertise needed to design, deploy, and interpret these systems. Organizations need professionals who understand both the mathematical underpinnings of advanced analytics and the business contexts in which they operate. One particularly compelling example of prescriptive analytics in practice is how airlines optimize their pricing strategies. These systems continuously adjust ticket prices in real time based on complex algorithms that process enormous volumes of data. When a competitor drops their fare on a specific route, the system automatically calculates whether matching the price will maximize revenue or if maintaining current pricing is more profitable based on projected demand patterns. Similarly, if booking velocity suddenly increases for a particular flight, the system can recognize this demand spike and incrementally raise prices to capture additional revenue without deterring too many potential customers. What makes prescriptive analytics simultaneously the most valuable yet challenging type of analytics to implement is the integration complexity required to create a functioning system. Organizations must have mastered data collection, cleaning, and integration, developed robust predictive modeling capabilities, defined clear business rules and constraints, and built the technical infrastructure to execute recommendations in near real time. The systems must also maintain transparency so that human decision makers can understand and trust the recommendations, particularly in high-stakes scenarios. This complexity explains why relatively few organizations have fully realized the potential of prescriptive analytics. Many struggle with data quality issues that undermine the accuracy of underlying predictions. Others lack the cross-functional collaboration needed to translate analytical insights into operational actions. Technical silos often prevent the seamless integration required for prescriptive systems to access all relevant information. And in some cases, organizational resistance to algorithmic decision-making creates barriers to adoption. Despite these challenges, the trajectory is clear. As competitive pressures intensify and technology continues to advance, prescriptive analytics will increasingly become a requirement for organizations seeking to optimize performance in complex, rapidly changing environments. The companies that master this capability will be able to navigate uncertainty with greater confidence, responding to emerging opportunities and threats with speed and precision that manual decision processes cannot match. The gap between companies struggling with basic reporting and those dominating their markets isn't just technological, it's philosophical. What if I told you that industry leaders don't see analytics as four separate disciplines, but rather as a single interconnected system where each layer builds upon the previous? Their success stories reveal a pattern hiding in plain sight. When we examine how industry titans deploy analytics, we discover they've created ecosystems where descriptive, diagnostic, predictive, and prescriptive capabilities function as complementary forces rather than isolated tools. This integrated approach transforms data from a passive resource into an active decision engine that powers their competitive advantage. Unfortunately, this integrated vision remains elusive for many organizations. The reality on the ground often looks quite different. Fragmented analytics teams working in isolation, using incompatible systems, and rarely sharing insights across departmental boundaries. Marketing might leverage sophisticated predictive models, while operations remains stuck with basic reporting dashboards. The finance team might build intricate forecasting tools while customer service relies on intuition rather than data. This disjointed approach severely limits the potential value of analytics investments. Let's examine how the analytics pyramid manifests in different industries, starting with retail, a sector that has been revolutionized by data-driven decision-making. In retail, the foundation begins with descriptive analytics through comprehensive sales reporting. Major retail chains meticulously track monthly sales patterns, revealing critical trends like declining desktop computer purchases alongside rising tablet sales. This historical performance data creates the essential baseline for all subsequent analysis. Building on this foundation, retailers employ diagnostic analytics to understand the underlying drivers of consumer behavior. When a retailer notices an unexpected spike in vegan product sales, they can investigate further to discover correlations with specific marketing campaigns that emphasized health benefits. This insight goes beyond simply knowing what happened to understanding why it happened, enabling the retailer to make informed inventory adjustments. With a solid understanding of past performance and causal relationships, leading retailers then implement predictive analytics to anticipate future customer behaviors. By analyzing historical purchasing patterns, they can identify which customers show early warning signs of disengagement, allowing for proactive retention strategies before these customers actually stop shopping with them. This shift from reactive to proactive management represents a crucial competitive advantage. At the pinnacle of retail analytics maturity, prescriptive systems deploy sophisticated algorithms that automatically optimize business operations. Dynamic pricing systems exemplify this capability, continuously adjusting product prices based on real-time demand signals, competitive positioning, and individual customer behavior. These systems don't just inform decisions, they make them, enabling retailers to maximize revenue in ways that would be impossible with manual approaches. The healthcare industry presents another compelling example of the analytics pyramid in action with life-changing implications beyond profit margins. Healthcare organizations begin their analytics journey by summarizing patient records through descriptive analytics. These systems catalog historical treatments, outcomes, and demographic information, creating a comprehensive view of patient populations and treatment effectiveness. This retrospective analysis establishes critical baselines for measuring improvements in care quality. Diagnostic analytics takes healthcare data deeper by identifying patterns in diagnosis and treatment outcomes. Hospitals analyze which interventions produce better results for specific patient segments, discovering that certain treatments show higher efficacy rates among particular demographic groups. These insights allow medical professionals to tailor their approaches based on evidence rather than intuition alone. As healthcare organizations advance up the analytics pyramid, predictive capabilities enable them to identify patients at elevated risk for specific conditions or complications. By analyzing treatment history alongside demographic data, hospitals can forecast which patients face higher readmission risks, enabling targeted interventions that improve outcomes while reducing costs. This proactive approach transforms care delivery from reactive treatment to preventative health management. At the prescriptive level, healthcare analytics recommends personalized treatment plans based on individual patient profiles. Advanced algorithms consider a patient's unique health data, comparing it against millions of similar cases to suggest the optimal course of action. Rather than relying on standardized protocols, these systems enable truly personalized medicine that accounts for the complex interplay of factors affecting each patient's health. The financial services industry provides our third example, where analytics has fundamentally transformed risk management and customer relationships. Financial institutions begin with descriptive analytics for transaction monitoring, tracking, and reporting on financial activities across their customer base. These systems establish the historical record of account activity, payment processing, and investment performance that forms the bedrock of financial oversight and regulatory compliance. Diagnostic capabilities then help financial services firms detect anomalies that might indicate fraudulent activity. By analyzing transaction patterns and identifying unusual behaviors that deviate from established norms, these systems protect both institutions and customers from financial losses. This level of analysis transforms raw transaction data into meaningful insights about potential threats. Predictive analytics enables financial services companies to assess credit risk with unprecedented precision. By analyzing historical repayment behavior alongside thousands of other variables, institutions can forecast which loan applicants are most likely to default, leading to more informed lending decisions that reduce risk while expanding credit access to qualified borrowers. At the prescriptive level, financial analytics optimizes investment portfolios by recommending asset allocations tailored to individual risk tolerances and market conditions. These systems continuously evaluate market trends, economic indicators, and individual investor preferences to suggest portfolio adjustments that maximize returns while managing risk. This capability transforms wealth management from an art to a science, enhancing investment performance through data-driven decision-making. What makes these industry examples so powerful is how each organization builds upon its analytics foundation in a logical progression. They don't treat these capabilities as separate, unrelated tools. Instead, they create an integrated analytics lifecycle where insights flow naturally from one level to the next. Descriptive analytics reveals what happened, diagnostic analytics explains why it happened, predictive analytics forecasts what might happen next, and prescriptive analytics recommends how to respond optimally. This integrated approach yields substantial competitive advantages. Retailers with mature analytics ecosystems achieve profit margins up to 60% higher than their less data-savvy competitors. Healthcare organizations report improved patient outcomes alongside cost reductions of 15 to 25%. Financial institutions with sophisticated analytics capabilities demonstrate greater resilience during market volatility while maintaining stronger customer relationships. While all industries benefit from enhanced analytics capabilities, certain sectors are experiencing particularly dramatic transformations. Retail leads the pack in prescriptive implementations, with dynamic pricing and personalized recommendation engines reshaping consumer experiences. Healthcare shows the most significant impact in predictive applications, where early intervention based on risk modeling directly improves patient outcomes. Financial services demonstrates the strongest benefits in diagnostic analytics, where fraud detection systems save billions annually. Manufacturing represents an emerging frontier with Internet of Things, IoT sensors generating unprecedented volumes of operational data. As these companies progress up the analytics pyramid, they're achieving remarkable efficiency gains through predictive maintenance and automated quality control. Transportation and logistics firms are similarly transforming through route optimization algorithms that continuously adjust to changing conditions in real time. What distinguishes analytics leaders across all these industries isn't just their technological sophistication, it's their organizational approach. They've cultivated analytics cultures where data literacy spans from the front line to the C-suite. They've implemented governance frameworks ensuring data quality and accessibility. Most importantly, they've aligned their analytics capabilities with strategic priorities, ensuring that technological investments directly support business objectives. Even with the right analytics culture, many organizations stumble at a critical decision point that determines success or failure, selecting which analytics approach to apply to a specific business challenge. Why do some analytics initiatives deliver transformative results while others barely move the needle despite similar investments in technology and talent? The answer often lies not in the quality of the analysis, but in the crucial step of matching the right analytical approach to the business question at hand. This decision point represents the invisible barrier between analytics success and failure. Selecting the wrong approach can lead to wasted resources and missed opportunities regardless of technical expertise or data quality. It's like having a complete toolbox, but choosing a hammer when you actually need a screwdriver. The tool itself works perfectly, but it's simply the wrong one for the job. Consider this common scenario. A marketing team struggles to understand why their latest campaign underperformed. They immediately commission sophisticated predictive models to forecast future campaign results, but what they actually need first is basic diagnostic analysis to understand what went wrong with the current campaign. Without diagnosing the problem, any predictive work rests on a flawed foundation. Fortunately, there's a straightforward framework to help match business questions to the appropriate analytics type. It begins with understanding what question you're truly trying to answer. If you're asking what happened, your need is descriptive analytics. When asking why did this happen, turn to diagnostic analytics. Questions about what might happen in the future require predictive approaches, and when you need to determine what action should we take, that's the domain of prescriptive analytics. This decision tree provides clarity during those crucial moments when you must determine which analytical path to pursue. A retail manager wondering about last quarter's sales performance needs descriptive analytics to summarize the results. If that same manager wants to understand why sales declined in specific store locations, diagnostic analytics becomes essential. To forecast next quarter's performance, predictive analytics comes into play. And when determining optimal inventory levels or pricing strategies, prescriptive analytics offers the most value. The consequences of selecting the wrong analytics approach extend far beyond operational inefficiency. A company might invest heavily in predictive analytics without first understanding historical patterns through descriptive analytics, resulting in inaccurate forecasts built on incomplete foundations. This mismatch between analytics capability and business need often leads to poor decision-making that can impact an organization's competitive position and financial health. Organizations must also honestly assess their readiness for each analytics level before implementation. This assessment should evaluate three key elements: current data infrastructure, team skill sets, and the availability of necessary tools. For example, a company must ensure they have clean historical data before attempting descriptive analytics, let alone more advanced approaches. Without establishing this foundation, efforts to implement more sophisticated analytics will likely fail. The infrastructure, tools, and skills needed vary significantly across the analytics pyramid. Descriptive analytics requires relatively straightforward reporting tools and basic data visualization skills. Most organizations already have access to spreadsheet applications and business intelligence platforms that can handle these needs. The necessary skills include data cleaning, basic statistical understanding, and the ability to create meaningful visualizations that communicate findings effectively. As organizations move up the pyramid, requirements become more specialized. Diagnostic analytics demands more advanced statistical tools and analytical capabilities. Team members need stronger statistical backgrounds to perform correlation analyses and identify potential causal relationships. Tools like R and Python become increasingly important, along with more sophisticated business intelligence platforms that support drill-down functionality. Predictive analytics represents a significant jump in technical requirements. Machine learning expertise becomes essential, along with specialized software platforms that support model development and deployment. Data scientists with programming skills and statistical knowledge are typically needed, although newer automated machine learning tools have begun making predictive capabilities more accessible to analysts without extensive coding experience. At the pinnacle, prescriptive analytics requires knowledge of optimization algorithms and decision-making frameworks. The technical bar is highest here, often requiring specialized expertise in operations research, simulation modeling, and advanced mathematics. Team members need to understand both the technical aspects of optimization and the business context in which recommendations will be implemented. One of the most challenging aspects of analytics implementation is explaining these technical concepts to non-technical stakeholders who ultimately make resource allocation decisions. The key lies in using clear, relatable language and effective visual aids rather than technical jargon. For instance, when explaining the difference between predictive and prescriptive analytics to executives, you might compare predictive models to weather forecasts. They tell you it will rain tomorrow. And prescriptive systems to navigation apps. They tell you which route to take to avoid the rain. Simple analogies bridge the gap between complex analytics concepts and stakeholder understanding. Descriptive analytics can be compared to reviewing the box score after a sports game. It tells you what happened, but not why one team won. Diagnostic analytics is like a sports analyst breaking down the key plays that determined the outcome. Predictive analytics resembles betting odds for future games, while prescriptive analytics is the specific game plan a coach develops to maximize chances of winning. Organizations can leverage assessment tools to evaluate their analytics readiness more systematically. Maturity models help identify gaps in skills, tools, and processes necessary for effective implementation at each level. These assessments typically evaluate dimensions such as data quality, analytical capability, technical infrastructure, and organizational alignment. The results provide a roadmap for developing capabilities in a logical sequence rather than attempting to implement advanced analytics without the necessary foundation. When determining which analytics type best fits a specific business challenge, organizations should consider the time horizon of the decision, available data quality and quantity, and the decision's strategic importance. Operational decisions with short-term impacts might benefit most from descriptive and diagnostic approaches, while strategic decisions with longer-term implications often justify investment in predictive and prescriptive capabilities. Organizations should also consider the cost-benefit ratio of different analytics approaches. As you move up the pyramid, implementation costs increase substantially, requiring careful evaluation of potential returns. A simple diagnostic analysis might provide 80% of the value at 20% of the cost of a sophisticated prescriptive system in some business contexts. The key is matching the analytical approach to the decision's importance and complexity. Implementation timelines also differ significantly across analytics types. Descriptive analytics can often be implemented in weeks, while comprehensive prescriptive systems might require months or even years of development. Organizations with urgent business challenges should consider starting with simpler approaches that deliver quick wins while building toward more advanced capabilities over time. The business context also matters tremendously. Some industries, like financial services, have long-standing experience with advanced analytics and well-established methodologies, while others are just beginning their analytics journey. Organizations should benchmark their analytics ambitions against industry norms while also identifying opportunities to gain competitive advantage through more sophisticated approaches where competitors haven't yet ventured. Testing provides another valuable approach to determining the right analytics type. Rather than committing fully to a comprehensive analytics initiative, organizations can run pilot projects that apply different analytics approaches to a specific business challenge. These pilots provide concrete evidence of which approach delivers the most value in the organization's specific context, reducing implementation risk. Cross-functional teams make better decisions about analytics approach selection than either technical or business teams working in isolation. Technical experts understand what's possible, while business leaders understand what's valuable. Bringing these perspectives together ensures that analytics initiatives address genuine business needs with appropriate technical solutions rather than pursuing technology for its own sake. Organizations that successfully navigate analytics selection decisions share several common traits. They maintain a clear focus on business objectives rather than technical sophistication. They understand their current capabilities and limitations, and they take an iterative approach that builds capabilities progressively rather than attempting to implement advanced analytics without the necessary foundation. This approach to building analytics capabilities might seem counterintuitive at first. While many organizations rush towards sophisticated predictive models and AI-powered solutions, they're actually creating a precarious structure that often collapses under its own weight. The most successful data-driven companies understand something crucial. Analytics capabilities must be built methodically like a pyramid, starting with a solid foundation. The question every organization should ask isn't how quickly can we implement advanced analytics, but rather which analytics capability should we focus on developing first? This seemingly simple question reveals a critical mistake most organizations make. Pursuing capabilities in the wrong order, creating technical debt that undermines their entire analytics strategy. Think of analytics capability building as constructing a house. You wouldn't start by installing the roof before laying the foundation. Yet, this is precisely what happens when organizations attempt to implement predictive or prescriptive analytics without mastering the fundamentals of descriptive and diagnostic analytics. This misalignment creates not just technical problems, but organizational confusion that derails even the most promising analytics initiatives. A strategic roadmap for analytics capability building always begins with mastering descriptive analytics. This foundational level serves as the bedrock upon which all subsequent analytics types depend. Without reliable, clean data and the ability to effectively summarize what happened, organizations cannot accurately diagnose why it happened, predict what might happen next, or prescribe optimal actions. Consider the practical implementation of this roadmap. In the initial stage, organizations should focus on establishing data collection mechanisms, implementing basic data governance frameworks, and developing straightforward reporting capabilities. This might involve standardizing metrics definitions across departments, cleaning historical data, and creating dashboards that provide a single source of truth for the organization. Once the descriptive foundation is solid, the next stage involves building diagnostic capabilities. This requires more sophisticated data integration, statistical analysis skills, and the ability to drill down into aggregated metrics. Organizations at this stage typically invest in more advanced analytics tools and begin hiring analysts with stronger statistical backgrounds who can identify correlations and perform root cause analysis. The progression to predictive capabilities represents a significant leap in analytics maturity. This stage often requires specialized skills in statistical modeling and machine learning, along with more robust data infrastructure capable of handling larger volumes and varieties of data. Organizations successfully making this transition typically invest in data science talent and begin developing the technical infrastructure needed to deploy models into production environments. Finally, organizations reaching prescriptive analytics capabilities combine predictive insights with optimization algorithms and decision frameworks. This highest level of the analytics pyramid requires not just technical sophistication, but also organizational processes that can translate analytical insights into operational actions. Few organizations reach this level of maturity as it requires seamless integration between technical systems and business processes. To determine your organization's current analytics maturity, conduct an honest assessment of your existing data practices, tools, and team capabilities. Ask questions like, can you reliably access clean, consistent data across the organization? Do you have standardized reporting that stakeholders trust? Can your team explain why metrics change over time? Can you forecast future outcomes with reasonable accuracy? Can your systems automatically recommend optimal actions based on predictions? These questions help identify gaps in your analytics capabilities and prioritize which areas to develop first. Many organizations discover they've attempted to build advanced capabilities on shaky foundations, explaining why their analytics investments haven't delivered expected returns. Building the right team is equally critical to developing analytics capabilities. Different stages of analytics maturity require different skill sets. At the descriptive level, you might need business analysts who understand how to gather requirements and create simple dashboards. The diagnostic stage typically requires data analysts with stronger statistical skills and the ability to investigate complex business problems. As you move toward predictive capabilities, data scientists become essential professionals with expertise in statistical modeling, machine learning algorithms, and programming languages like Python or R. The prescriptive stage might require operations research specialists familiar with optimization techniques, along with software engineers who can implement complex decision systems. Technology requirements also evolve as you progress through the analytics maturity model. Initial descriptive capabilities might be built using spreadsheets and basic visualization tools. Diagnostic capabilities often require more sophisticated business intelligence platforms with drill-down capabilities. Predictive analytics typically demands specialized statistical software or machine learning platforms, while prescriptive systems might require custom-developed optimization engines integrated with operational systems. Organizations face numerous challenges when developing analytics capabilities. Resistance to change often tops the list. Employees accustomed to making decisions based on intuition may resist data-driven approaches. This cultural resistance can undermine even technically sound analytics implementations. Another common challenge is the lack of data literacy among staff. Even with sophisticated analytics capabilities, organizations struggle to create value if employees cannot understand and act on insights. Investing in training programs that build data literacy across the organization can help overcome this challenge. Insufficient investment in technology and training also hinders analytics capability development. Organizations often underestimate the resources required to build robust analytics capabilities, leading to partial implementations that fail to deliver value. Successful organizations recognize that analytics capability building is a long-term investment requiring sustained commitment. Organizational silos present another significant challenge. Analytics capabilities often span multiple departments, requiring collaboration between IT, business units, and specialized analytics teams. Breaking down these silos is essential for creating integrated analytics capabilities that deliver organization-wide value. Case studies of companies that have successfully built analytics capabilities from scratch consistently highlight the importance of starting with a strong foundation in descriptive analytics. These organizations typically demonstrate a disciplined approach to capability building, investing in each stage before advancing to the next. For instance, a mid-sized manufacturing company began its analytics journey by standardizing production metrics across facilities. Once they established reliable descriptive reporting, they progressed to diagnostic analytics to understand variations in production efficiency. This foundation allowed them to later implement predictive maintenance models that forecast equipment failures before they occurred. Eventually, they developed prescriptive systems that automatically adjusted production schedules to optimize efficiency. This staged approach allowed the company to realize benefits at each level while building toward more sophisticated capabilities. Importantly, each stage built upon the previous one, creating a coherent analytics ecosystem rather than disconnected point solutions. Expert advice consistently emphasizes the need for organizations to focus on building analytics maturity in stages rather than attempting to implement all analytics types simultaneously. This approach allows for better resource allocation, skill development, and organizational learning. So, which analytics type should you focus on first? For most organizations, the answer is descriptive analytics, mastering the art of accurately reporting what happened before, attempting to explain why it happened or predict what might happen next. This foundation first approach might seem less exciting than jumping straight to advanced machine learning, but it dramatically increases the likelihood of analytics success. For individuals building careers in data, a similar progression makes sense. Mastering descriptive analytics builds essential skills in data manipulation, visualization, and business communication that remain valuable throughout an analytics career. As you develop these foundational skills, you can progressively add capabilities in diagnostic, predictive, and eventually prescriptive analytics. The key insight here is that analytics capability building is a journey, not a destination. Even organizations with mature analytics capabilities continually refine their approaches and adapt to new technologies and business challenges. The most successful organizations view analytics capability building as an ongoing process of evolution rather than a one-time implementation project. As organizations continue refining their analytics capabilities, an unprecedented transformation is reshaping the entire analytics landscape. While companies meticulously build their analytics maturity one level at a time, AI integration is simultaneously erasing the distinctions between these levels. creating a future where analytics types converge rather than stack, challenging our fundamental understanding of analytics evolution. This convergence is happening right before our eyes. Traditional analytics approaches required specialized expertise at each level of the pyramid, but AI and machine learning are democratizing access to sophisticated capabilities. Take predictive analytics, once the exclusive domain of data scientists with advanced degrees. Today, tools like PKN are enabling business users to formulate predictive questions without extensive technical expertise. A marketing manager can now predict customer churn by simply interacting with an AI interface that guides them through the process, generating the necessary SQL notebooks to train machine learning models behind the scenes. What's remarkable about this shift is how it fundamentally changes who can participate in advanced analytics. No longer do organizations need to hire teams of specialized data scientists to implement predictive capabilities. Instead, the subject matter experts who understand the business questions can directly engage with AI-powered systems to get the answers they need. But this raises a profound question. As AI increasingly automates the technical complexity that once separated the different analytics types, will the pyramid structure we've carefully built become obsolete, or will these technological advances simply enhance and strengthen the existing framework? The evidence suggests that rather than making the analytics pyramid obsolete, AI integration is actually reinforcing its fundamental structure while blurring the boundaries between levels. Expert predictions indicate that AI will enhance the pyramid by providing deeper insights and more sophisticated capabilities at each level, while making transitions between levels more fluid and accessible. Consider how automated insights, one of the emerging trends in AI-powered analytics, are transforming descriptive analytics. Traditional dashboards required users to manually identify patterns and anomalies in data. Now AI can automatically detect significant changes in metrics, unusual patterns in customer behavior, or outliers in operational data, bringing a diagnostic element directly into descriptive reporting. The system doesn't just show what happened, it proactively identifies what matters. Continuous intelligence represents another significant trend where real-time data streams are constantly analyzed to detect patterns and trigger immediate actions. This creates a seamless flow from descriptive observation to prescriptive recommendation without distinct stages in between. A manufacturing operation using continuous intelligence doesn't wait for monthly reports to identify equipment issues, then analyze why they occurred, predict future failures, and finally recommend maintenance schedules. Instead, the entire process happens in a continuous loop with sensors monitoring equipment performance, AI models predicting potential failures, and automated systems scheduling maintenance, all without human intervention. Augmented analytics, where AI assists human analysts by suggesting relevant visualizations, uncovering hidden patterns, and automating routine analytical tasks, further blurs the lines between analytics types. When an analyst investigates a sales decline, an augmented analytics system might automatically identify contributing factors, diagnostic, forecast future impacts, predictive, and suggest mitigation strategies, prescriptive, all within a single interface. These advances are creating what we might call analytics convergence, where the traditional pyramid structure remains conceptually valuable, but the boundaries between levels become increasingly permeable and fluid. Organizations still need to understand the difference between describing what happened and predicting what will happen, but the technical barriers separating these capabilities are rapidly dissolving. This convergence is particularly evident in how AI is making advanced analytics accessible to non-specialists. Previously, the progression from descriptive to prescriptive analytics required organizations to build increasingly specialized teams with advanced technical skills. Now, generative AI capabilities in tools like can guide users through complex analytical processes. A business user can pose a question in natural language, and the AI system will translate it into the appropriate analytical approach, whether that's a simple trend analysis or a complex predictive model. For example, a retail manager might ask, which customers are most likely to stop shopping with us in the next month? The system can recognize this as a predictive question, guide the user through selecting relevant variables, generate the appropriate machine learning model, and present the results in an intuitive format, all without requiring the user to understand the technical details of how prediction works. This democratization of advanced analytics is perhaps the most transformative aspect of AI integration, as it removes the steep capability curve that previously prevented many organizations from climbing the analytics pyramid. However, this rapid transformation brings significant ethical considerations that organizations must address. As analytics becomes increasingly automated, the transparency of decision-making processes becomes a critical concern. When an AI system recommends firing certain employees because they match patterns associated with poor performance, can the organization explain how that decision was made? The black box nature of many advanced AI systems creates accountability challenges that must be addressed through ethical frameworks and governance structures. Bias in algorithms represents another serious ethical challenge. If predictive models are trained on historical data that reflects past discriminatory practices, they may perpetuate or even amplify these biases in their recommendations. For example, a loan approval system trained on historical lending data might inadvertently discriminate against certain demographic groups if those patterns existed in the training data. Organizations implementing AI-powered analytics must prioritize fairness and accountability by regularly auditing their systems for bias and implementing safeguards against discriminatory outcomes. Despite these challenges, the vision for future analytics systems is compelling. Seamless integration of all four analytics types, allowing organizations to leverage descriptive, diagnostic, predictive, and prescriptive capabilities in a cohesive manner. This integration enables businesses to respond more dynamically to market changes and customer needs, creating a continuous feedback loop where insights automatically trigger actions and the outcomes of those actions generate new insights. Imagine a retail operation where inventory systems not only track current stock levels, descriptive, and identify factors contributing to stock outs, diagnostic, but also predict future demand patterns, predictive, and automatically adjust purchasing and distribution, prescriptive, all without requiring separate teams or systems for each function. This integrated approach allows the business to operate with unprecedented agility, responding to changing conditions before they become problems. Or consider a healthcare provider using an integrated analytics platform that monitors patient vital signs in real time, descriptive, identifies concerning patterns, diagnostic, predicts potential complications, predictive, and recommends preventive interventions, prescriptive. Instead of treating these as separate analytical processes requiring different specialists and systems, the entire analytical workflow becomes a seamless continuum, with each insight flowing naturally into the next. This vision represents the ultimate evolution of the analytics pyramid, not its obsolescence, but its transformation into a more dynamic and accessible framework. The hierarchical relationship between the different analytics types remains conceptually important as each builds upon the insights of the previous level. But the technical and organizational barriers between levels are dissolving, allowing organizations to move fluidly between describing the past, understanding the present, and shaping the future. For data professionals navigating this changing landscape, the implications are profound. The technical skills that once defined different roles in the analytics hierarchy, data analysts focused on reporting, data scientists building predictive models, operations researchers developing optimization algorithms, are increasingly being augmented or automated by AI. This doesn't mean these roles will disappear, but rather that they'll evolve to focus more on problem framing, ethical considerations, and strategic implementation rather than technical execution. The most valuable skill in this new landscape will be the ability to ask the right questions and interpret the answers in meaningful business contexts. As AI handles more of the technical complexity, human experts will need to focus on understanding the business problems to be solved, ensuring the ethical implementation of automated systems, and translating analytical insights into strategic action. For organizations, the key takeaway is that building analytics capability is still a journey that requires thoughtful planning and strategic investment. The analytics pyramid remains a useful framework for understanding the progression of analytical maturity, but AI integration allows organizations to navigate this journey more quickly and with fewer specialized resources than ever before. The future belongs to organizations that can harness this convergence to create truly integrated analytics ecosystems where descriptive insights automatically trigger diagnostic investigations, which feed into predictive models, which drive prescriptive recommendations, all within a cohesive and accessible framework that empowers decision makers throughout the organization. And there you have it, the complete picture of the analytics evolution pyramid that can fundamentally transform how your organization leverages data. The journey from descriptive to prescriptive isn't just a technical progression, it's a strategic advantage that pays dividends. Recent research reveals organizations effectively implementing advanced analytics achieve 5-6 times higher ROI compared to those stuck at basic levels. This isn't just about having fancier tools, it's about building capabilities systematically. Expert insights consistently emphasize that comprehensive analytics capabilities are critical for making truly informed decisions and driving strategic growth. The power lies not in rushing to the top of the pyramid, but in methodically mastering each level. So, what's your next move? Take a moment to honestly assess your current analytics approach. Identify where you stand in the pyramid and what concrete steps you can take to reach the next level. Your analytics evolution starts now.